Hello and welcome to XDRI attacks and how to enhance resilience of residential routers. I'm Philipp Jeitner and I wrote this paper together with Haya, Shulman, Teichmann and Waidner. So first, to give you an overview over the coming talk, I'll just quickly go over the topics. So first we will look at DNS and residential routers, what it is and what they do. Then we will look at the attacker models which we considered for our attacks. I'll present you the 4 attacks we evaluated in the routers we bought, and then I will talk about the black box and white box evaluation we did against the routers. We will talk about if we actually need those DNS implementations in the routers or if we maybe get rid of them for basically reduced attack surface. And finally, I'll present our disclosure efforts and some conclusion. So first, what is DNS in residential routers? So the DNS is the domain name system, which you probably know for resolving domain names to IP addresses. And in the context of residential routers, essentially there are clients which send their DNS requests to routers. The routers forward the requests to the ISPs or a public resolver if you use those. And those resolvers then query the authoritative name servers and provide the actual data. And typically the router as well as the client are auto-configured. Client is auto-configured via DHCP and the router is auto-configured by the ISP depending on what protocol it uses to connect to the internet. And if we talk about attacks against the DNS and routers, we mostly consider cache poisoning attacks. So these attacks are essentially, the goal is to associate a victim domain with the attacker's address, and this allows traffic hijacking because then the traffic which should go to the victim actually goes to the attacker and the attacker might do something with it. Right, so first, considering attacker models, we have 2 attacker models. The first one is the model of a malicious script, essentially a website controlled by the attacker, which the victim visits on a laptop or something. And this website can only trigger typically standard A queries via the browser, maybe via JavaScript or just by embedding images, etc. The second attacker model is that of a malicious client. For example, if you have a public Wi-Fi, it might be a laptop which can just join the network, or if you have a bigger network, maybe like on a campus network, there are a lot of potentially malicious clients which could connect to the network. And these malicious clients then can send arbitrary DNS messages, including unusual queries which you couldn't do via a browser, or even malformatted queries which aren't actually valid and might trigger problems in the resolvers. For the attacks we considered, essentially we evaluated 4 attacks and vulnerabilities in the routers we bought. Some of them are new, some of them are improved, and some of them are already known. The first attack is cache poisoning via character misinterpretation. And in this attack, essentially the goal of the attacker is to inject a poisonous query by providing a name, in this case victim.com, including a 0 byte, and then attacker.com. And this might trigger a vulnerability in the router, which essentially truncates this name, which is owned by the attacker, down to victim.com and then associates victim.com with the IP address of the attacker. The second attack we considered is transaction ID forwarding. And in this case, which we found in some routers, the routers essentially forward the transaction ID used by the client, but still implement a cache. So essentially, this means that if the client is malicious, he can essentially communicate the transaction ID which he uses to an outside attacker in the internet, and then the outside attacker can basically inject DNS messages into the communication between the router and the upstream resolver because he knows the transaction ID and the UDP source port is not enough to protect against injection attacks. The same is essentially true of SETI UDP source port, which is probably the oldest known way of doing DNS cache poisoning practically, where the router just uses a static UDP source port. And so the only thing which prevents off-path injection is the transaction ID, which doesn't provide enough entropy to actually protect against attacks. And finally, the 4th attack, which we considered, is checking disabled forwarding, which is a flag in the DNS header, which essentially tells a resolver to disable DNSSEC processing. And so what some routers do is essentially they forward queries which have this flag set to the upstream resolver, which tells the upstream resolver to disable DNSSEC checking. And then if the attacker manages to attack the communication between the upstream resolver and the name servers, essentially what happens is that the router gets the unchecked result because the attack doesn't basically trigger the validation because the validation was turned off by the bit. And because the router doesn't understand what this flag means, it caches the result and provides it even to clients which don't set the flag, which then means that the cache becomes poisoned. Right. So to evaluate these attacks, we did black box evaluation tests and also internet scans. And what we did is basically we started with an internet-wide scan of 1.5 million resolvers, basically all open resolvers in the internet. And in this scan, we found that 8.1% of the open resolvers in the internet were vulnerable to the misinterpretation attack, which we found last year and presented it at USENIX. And our data suggested that the vulnerability was in forwarders, so in like DNS resolvers, which don't directly send the requests to the name server, because we can see that because we run the name server for the test, but they send it to somewhere else, and then this somewhere else, often it's the Google public resolver, for example, sends the actual requests to the name servers. And so this gave us the idea to basically take a look at less known DNS implementations and forwarders. And one deployment of typically such forwarders are in home routers. And so essentially we designed a study and bought 36 physical devices and tested the 4 attacks against them and found that actually 15 of them are vulnerable to one of those attacks. You can see which one was vulnerable to which attack in the table. And essentially this shows that these vulnerabilities are kind of widely in these devices. And to show that they are actually deployed and used in the internet, we also did an ATHENE study, which was aimed to fingerprint the administrative interface of those routers and essentially locate clients with ATHENE advertisements, which actually use those routers we found vulnerable in our lab study. And we found actually a lot of devices or a lot of users which use such devices, which shows that these routers are actually widely used. Right, so to find out what causes the issue and to get some more information about it, we also did a white box evaluation where we essentially reverse engineered the firmware of the router, and the goal here was to verify programming mistakes which causes the vulnerability. And we found that basically many of those vulnerabilities are caused by somewhat naive programming mistakes. So essentially, if you just implement the basic DNS forward and you don't read a lot of security advisories or something, then these vulnerabilities might something which you do because it's just something you might not be aware of. And we also found that many of the forwarders aren't really written professionally. So many of the routers used open source components which aren't maintained since like 2000 or something. And we also found things like random number generators seeded with the device clock, but the device clock isn't actually initialized at the point where the forwarder started. So essentially the number generator always generates the same value, so the source port is always the same. And finally, we also did a study of GitHub forwarders. So we basically scanned or searched GitHub for DNS forwarders, which aren't like big implementations, but small implementations. Some developers just wrote, maybe to learn something, or maybe they had some special application where they use it. And we found that they contain the same vulnerabilities in 8 of the 10 cases we tested. And this essentially shows that this is not necessarily a problem of DNS implementations in routers, but also it's like just a problem of less popular DNS implementations, which maybe are implemented by developers which aren't really aware of the DNS ecosystem, or they don't really know a lot about DNS security, etc. And so essentially to cope with this problem that, okay, now you can go to patch all these routers, and that's also what we are pushing the developers, but we thought again about maybe it's a better idea to not trying to chase all these new vulnerabilities, but to reduce the attack surface, because we thought about, do we really need the DNS in those, or the DNS implementation in those routers? And to cope with this, essentially the DNS provides two functionalities. The first one is caching, and caching is typically used to improve performance. However, we found that caching is not really needed in routers anymore because most clients contain caches on their own. So operating systems typically include a DNS cache, and all browsers also contain DNS caches. So to just speed up the DNS operations, you don't really need a cache in the router, because all it helps is basically if one client visits the website and then another client visits the same website in the same network in a rather short period of time, then you have a really small performance improvement, but otherwise all the other caches do the work anyway. So you don't really need the cache in the router. And the second problem the DNS in the router actually solves is the problem of network management separation. So essentially what we found is that typically you have a client, and the client is configured via DHCP, and the client expects the DNS server IP in the DHCP offer. And so what the router could do to basically not have to implement DNS is he could send the IP of the upstream resolver. However, then if the internet connection changes, this might lead to a problem where the router could not communicate the changed network configuration. And so basically our idea is to replace the error-prone caching forwarders with simple network address translation rule to basically get rid of this error-prone cache. And so finally, for some information about disclosure and the conclusion, we contacted all vendors prior to the publication, and the open source components especially unfortunately weren't patched because they're so old. And basically our conclusion is that cache poisoning is still a problem in routers and that those vulnerabilities are widespread. But however, it might be a good idea to remove DNS instead of just trying to patch everything, etc. This was my talk. Thank you and goodbye.